Yeah, good afternoon, everybody. It's my pleasure to be here and to present our research on the topic of ceramic mechanical properties here at the ASTM meeting. The presentation will be today about relating ceramic mechanical properties standards to advanced ceramics produced by lithography-based additive manufacturing. My name is Johannes Homer and I'm CEO of Lithoz. But first, before I start into the topic, please let me present a little bit about our company, that you know with who is presenting here and what are we dealing with. So here you see our team maybe 1 year ago. Currently we are more than 70 employees, nearly 80 employees here in Austria, Vienna, and as well we have a location in the United States, in Troy, New York State, Albany, where Sean Allen is managing this subsidiary. Lithoz is very clearly the market and innovation leader in the field of high performance ceramic printing, and we are offering a full solution along the process chain, which means we are providing the printer as well as the material and the respective software for the printers. We also do a lot of customized solutions, especially in terms of material, but also in terms of printers. Currently we have sold about nearly 80 machines worldwide, which means from Australia, Singapore, Japan, China, Europe of course, but also of course United States and South America. I think what's very important for us is, since we are working here with in a new field, is that we are thinking more in a partnership and more than in a machine supplier, and therefore we have 20% of our customers have more than one machine. And I think especially in an innovative area like it is, like 3D printing is, it's so important to work here along the whole process chain and to really make the customer successful, and if somebody is successful with his application, he needs to have more machines, and this is what we have seen so far. So as long as we can support them very well, and as long as we can engage ourselves here in this topic, we can make him much faster successful. Here you see some of our customers. So we are working, most of the partners we have from industry, so 2/3 are approximately from industry, for example Morgan or Ceramco or Cerix, which is a Bosch company, and also in the R&D side, first of all Fraunhofer IKTS, the most well-known ceramic research center. They have already 3 machines, but also Colorado School of Mines or Sandia National Labs. Orford University is also one of our customers. Yes, so we see we have a broad basis of our installed machines, and we have already a lot of experience. So we are nearly 10 years old and we have built up a huge experience in the field of ceramics additive manufacturing. So I think before we come into the research topic, I think it's also important to first understand a little bit the technology, what we are doing, how we are doing it, and then what is currently the state of the art. I think this is also very important to understand what have we already reached and what can be done in this technology. So first of all, this is for those who are familiar with ceramics, is nothing new. Ceramic forming is a 2-stage process, so it means it starts with the forming and then with the debinding and sintering. For those who are familiar with, not so familiar with ceramics, which are more familiar for 3D printing, is here we have to add another step, the debinding and sintering step. So we are working under room temperature and then have to transfer the part into the furnace to debind it and to sinter it, and then finally achieving the mechanical properties, the required mechanical properties. Our technology is working with light, so based on a lithography approach, we're using DLP as a structuring method. We are exposing from underneath, so where the light hits afterwards the material solidifies, and the part is built upside down. This approach has a lot of advantages. First of all, it's easy to use in industrial scale because you don't have so much inventory here in terms of slurry. So you can work with very little slurry, and you can make much preciser parts because you have no plate part contact. So we think, I mean, we have a lot of knowledge on also on different approaches. We have them all in-house in our labs, but we think that DLB in combination with exposure from the bottom is the easiest way to industrialize this technology. I don't want to go now into more detail. If you need more information, you can find a lot of information on our website or on YouTube. You can see videos how this technology works. But after this is, as I said, just the 3D printing. It will be transferred into the furnace where we have then the debinding, which means the UV curable binder is burnt off, and then we have the sintering where the parts shrink together and achieve the resulting mechanical properties or the resulting densities and strength. This is nothing special for the 3D printing approach. This is basically what every ceramic part has to go through, and therefore the ceramicists are well aware of this technology. But what is now possible? What can already be done? So there are a lot of different materials which are already available. As you can see here, Alumina, zirconia is available, but also porcelain, glass ceramics, as well as bone replacement material like tricalcium phosphate, hydroxyapatite, bioglass, as well as more difficult materials like silicon nitride or refractory materials, magnesia corderite, as well as piezoceramics, and as a special materials regolite, which is actually moon dust, which we have also worked on together with the European Space Agency. Another material very recently is what you can see here, a metal ceramic composite, a silicon infiltrated silicon carbide. Together with the Fraunhofer IKTS, we were able to produce these parts, which you can see here. This is also something very unique in this field. Basically, what we can do, we can use every powder as it's from conventional forming technologies, and since it's processed the same way as in conventional forming. So here you see also a comparison between the LCM technology and the isopressed technology, and what you see here, that there is no difference. So this is a Cylon, a silicon nitride, and here you see the microstructure as well as material properties, and you see the microstructure is the same as well as the material properties are also the same. So it's really comparable. This is nothing where additive manufacturing cannot deliver what what traditional forming technologies can deliver. So it's something where we can say the state of the art is that we can achieve the same or at least very similar properties as in conventional forming. Here you see as well some other ceramics which are also very common, alumina or zirconia. You see that the strengths, the densities are very comparable to conventional forming, and also just as a matter of fact, the surface roughness, as you also seen in the silicon infiltrated silicon carbide part, they are very smooth, and all the parts which you have seen here so far, they have not been polished or grinded. So this is the normal way of what we can achieve with our technology. I think also what's very important to show the quality of additive manufacturing is if you can make alumina translucent. So which means that if something is translucent, there can be no pores included, there can be no cracks, everything needs to be perfect, and this is what we could show. So here you see two different aluminas, two different thicknesses, and you can see that you can clearly read through it. And also on the left hand side, the green one is a yak material, where you can also see that you can read through that. And I think, you know, this is what I call it the Champions League of ceramic processing. So if you can make transparent or translucent alumina, you can really show that your process is working and that everything is in a good way. And I think, you know, this, for those who are already aware of these kinds of developments, you see that this is really the leading edge here in ceramic additive manufacturing. And also I think interesting in terms of resolution, what can be achieved here. Here you see two different lattice cylinders. So we have struts of 100 microns or even below 100 microns, so 50 to 85 microns. So one is in Z, the other one in Y direction. You can see that it's really a very, very high resolution, and the openings are in the range of 100 microns. And I think what you can also see here, that this technology is very, very reproducible. So we can achieve really tight tolerances, and we see this technology already in industry, in serial production, and there you have to fulfill all those requirements, and especially reproducibility, tolerances is a very big topic there. Just something which we have lately been working on is also very interesting. It's multi-material 3D printing. Here you see our Serafab Multi 2M30, where you have two beds with a cleaning station in between, where you can really print two materials in different layers or even in the same layer, as you can see here. For example, here you see on the left hand side zircon and alumina combined. So the Lithoz is here written in zirconia in the same layers as in alumina. You can also see on the very right hand side and the down below that you can also print the same two different materials in the same layer. And also the contamination, I think this is the key element here, is already under control. So we can really make sure that there is no cross-contamination between one material to the next material. I think this is a very cool application, this multi-material. You will see a lot more in the future here. A lot of things are coming up, and I'm really looking forward to working here into a new field with this multi-material approach. Yeah, now let me talk a little bit about the mechanical characterization of alumina. Why is it important? How to characterize it? I think we have here done a very, very nice study together with the Montanuniversität in Leoben, where we made very clear research on how to test and what to test. So first of all, we had two different sintering temperatures and holding times. So one was material A, which was held for 20 hours at 1500 degrees, and material B, which was held for 2 hours at 1650 degrees C. And then we had, of course, bending parts which we tested, which we orientated in three different axes. So we printed it in all the possible axes, in X, Y and Z. And here you have the red one is Z, Y is in blue, and the green one, Z, is in green. And yeah, this was the setup. And then first of all we took a look in the microstructure and the grain size. What is of course very clear is that the grain sizes are different because the twelling temperature was different. So we would have expected, and this is what we see here, that the lowered sintered ceramics have a much finer grain size and a much more even pore size distribution, whereas the materials sintered at higher temperature have a broader spectrum and a much coarser grains. But there's also a different intensity, of course. So we achieved 96% density and 98% density respectively. And what you can see here, and I think this is the big issue with additive manufacturing, that when you are not yet dense, you can still see the layer structure. It's still visible, because you have with every technology a certain inconsistency at the inhomogeneity at the border, the layer borders, and it is much smaller a higher pore concentration at the layer boundaries. And if you do not sinter it to full density, you still have this information left that this part is built up of layers. And as you can see here in the upper picture, it is clearly visible that you see this layered structure, whereas in the picture below, where we have 98% of the density, the pores are completely homogeneous distributed, and you cannot see that this part has been made by additive manufacturing, and this is exactly what you want to achieve. So, and now we look at the mechanical properties, namely at the strength. So first of all, what you can see here, that one thing which might be coming first out is that that you have the A material, which has actually a lower density, has a higher strength compared to the B material, and but the huge difference is here that the A material, sorry, what I forgot to mention is of course that both has been machined. So as a standard testing method, they have been machined and chamfered and then tested. Sorry, I forgot to mention this. But anyway, so we see machine the part which has actually a lower density has a higher strength, which is due to the smaller grain sizes. But what we can see here, and this is what you can see here from the Weibull picture on the left hand side, is that there is a clear difference between between Z and the other two axes in the A sample, whereas we don't see a significant difference in the B sample. And also, as you can see here from the Weibull modulus, also in the B sample, the Weibull modulus is much higher than in the A sample. So you're achieving quite high strength values, but the Weibull modulus is rather low, and the Z has a significant difference from X and Y. So again, why does this happen? Because we have smaller grain sizes, but the defects are still here, and when you test them, you can then find them more easily. And the B samples have a lower value in strength but a higher Weibull modulus, and there is no significant difference between all three axes. And if we compare now machined and as printed, again, so you already know the machined values from B, and if we measure them as printed, you can see that there is, at least from the Weibull statistics, a significant difference in the as printed value. But the difference is still not too big, but it's here. And Weibel modulus is getting a little bit lower. Also, the values are still comparable. They are still within the distributed strength, and there is not such a big impact on the machining. But you can see that at least in Z there is a difference. Why is this? This is very clear because we have the XY, we have a layer-wise printing. We see that there are layers, and these layers, they act then as a tension tip, and then we have there as a tension concentrator, and then we see that we have there higher stresses, and this decreases a little bit the strength of the material. So to conclude all this, I mean, very briefly say, okay, what is the outlook and what can we recommend? As a conclusion, first of all, what we have to say is basically, or nearly every ceramic material can be processed via additive manufacturing, although not every material is yet available, but still a lot of different materials are available. The LCM technology is clearly a technology which can produce strong and dense ceramics, and also, as you have seen, very high quality is also possible, and you can make, or we can make, also translucent alumina. And also the fine structures can be produced well below 100 microns, and last but not least, also multi-material printing is available. But what is now the recommendation how to really test additive manufactured parts? So our recommendation, this is what we are really trying to educate a little bit also the market, is what or how can it be tested. First of all, we prefer 4-point bending over 3-point bending, because it gives you a bigger volume which can be tested. And this is definitely a must, I would say, is to test all parts in upright position, so that that you are testing the layer adhesion. Usually this is the Z-axis. So you build the part like this, and then you can test it like this, and then you really test the layer adhesion. We strongly prefer that the test should be done machined, this is possible, but also, and this is very important, it should be done as printed, because if you have the actual part, you will not be able to machine it everywhere and to test it, and you will have a multi-material, a multi-axial, multi-axial tension, and then you have the as printed quality on your part. And so we strongly recommend to do also a as printing testing in order to really get the real values. And as we can see, as we have seen, the difference is not so big. So as printed is for sure a method which should be taken very much into consideration, and should also come, in our opinion, into a standard. Of course, I mean, the sample sizes are dependent what you have to use for your application, but basically there are already sample standards available, and you can use them, and the values, or I mean, of course, the values is what I pointed out already, they should be the same, but also the part geometry can be the same as in standard 4-point bending test. So I think this is very good and very important to discuss this in more detail. Definitely, if you have any questions, I will be here now to answer those questions, and for those questions which cannot be answered, please feel free to reach out to me. I think this is a very important topic which we need to discuss, and I would be very happy to follow up with you on this topic. Feel free to get in contact with us. I'm looking very much forward to hearing from you and looking forward to a vivid discussion. Thank you very much for your attention. Thank you very much for listening to this presentation, and hope to hearing from you soon. Thank you very much.